All right. So now getting to the PDEs, the first method we started is finite difference. Okay, so the most fundamental thing is how does finite difference approximate a PDE? So finite difference, if you look at the method itself, essentially stores the solution of the PDE on a bunch of grid points. So let's say if this is the solution u, x, you only store the values of u at these grid points. If the function evolves with time, then the solution at these points also evolves with time, right? So by storing the solution at grid points, you want to solve for a bunch of ODEs describing the evolution of these values. And in order for you to convert the PDE into an ODE, you have to approximate any derivative with respect to space using a finite difference scheme. That leads to the second question: what are some common finite difference approximations for the derivatives we commonly encounter? A first order derivative, du dx, can have forward, backward, and central differences, right? And the second order derivative also, we usually just have a single way to approximate it. It's a central difference and second order accurate. So that leads us to the third question: how to assess the accuracy of finite difference approximations. The technique we use really has no difference from the technique we use to assess the accuracy of a ODE integration scheme, right? Taylor series analysis, and you have to know how to figure out the order of accuracy by expanding the Taylor series to however many orders you need, and figure out the leading truncation error. Lastly, how to analyze the stability of finite difference schemes. We learned two methods, right? One method is to use a matrix stability analysis. That is to write the finite difference scheme approximation into a matrix equation, right? So after you discretize it, the PDE becomes a system of ODEs, and the system of ODEs can be written in a matrix form. The eigenvalue of the matrix gives you the stability of the finite difference scheme. We have studied briefly another way to analyze stability, that is using Fourier analysis, right? So just knowing the basic of Fourier analysis is important, and it's also important to know some basic outcome of the stability analysis. The basic outcome really has a more important consequence on the first order derivatives. So if you want to solve du dt plus a times du dx equal to 0, it turns out if a is greater than 0, the wave is traveling towards the right. You should be using a left biased scheme, right? A left biased scheme is stable. If a is less than 0, the wave travels towards the left, and the right biased scheme is stable. So this concept is called upwinding. You want to use a scheme that is biased towards the upwind direction. Another consequence of this is that through the eigenvalue analysis, we know that the eigenvalues comes out to be proportional, lambda being proportional to a over delta x, right? And if you use a explicit time integration scheme, so explicit, that means my lambda times delta t is going to determine the stability, right? So a times delta t over delta x is lambda delta t. So that's going to determine the stability of the ODE integration scheme. And this number sometimes called a CFL number, is something you should consider when selecting a ODE integration scheme when discretizing a first-order derivative in PDEs. Okay, so that's the stuff we learned about the finite difference. Now, finite volume. What kind of PDEs can finite volume solve? Oh, by the way, any questions for finite difference? Forgot to ask.